Welcome back, ladies and gentlemen. My name is Vamo Sama, and we are talking about probability and distribution in medical statistics. And this specific topic that we're going to talk about right now is about binomial and Poisson distribution, which are two different types of distribution. And we're also going to talk about them in detail. We're also going to take a look at the graphs of these distributions, and we're also going to talk about the formulas for binomial and Poisson distribution. So let's start off with binomial distribution and its formula. So it's a discrete type, it's a distribution for discrete variables, as we talked about the coin tossing examples in the previous lecture. So as number of coin tosses increases, it becomes difficult to list all possible arrangements. So we move on to a different type of analysis to calculate the probability, and for that we can use the formula for a binomial distribution. And formula for binomial distribution allows us to calculate probability of any particular value of the number of events, as long as we know the probability of success and the total sample size. So these two are the pre-requirements to be able to calculate the probability using binomial formula and binomial distribution. So here PR stands for probability of R events out of N is the total sample, and N is the sample or the sample size. So for example, number of coin tosses, if we are doing 2 coin tosses, then N would be 2, and R is the number of successes. Okay, so and P is the probability of success. So let's take an example and use this formula to calculate probability. So before we calculate the probability, this is how the binomial distribution looks. So as we keep on increasing the number of coins or the number of outcomes, we get more and more lines and bars, and they have different probabilities, and we need to calculate them. So this is how a binomial distribution looks, and when it keeps on increasing, it converts into a continuous type of distribution, which we will look into detail in the upcoming lecture. So that's how the binomial distribution actually looks like. But if you remember the last lecture, a simple 2 to 3 outcome distribution was just 2 or 3 lines. But as we keep on increasing the outcomes, then there is an addition of more and more bars or lines. So this here is the formula of the binomial distribution, or the binomial formula that we already discussed. So in this example, let's consider the total sample, or the total number of coin tosses. For example, let's take them as 2, and we are calculating the probability, or we use the formula to calculate the probability of getting 1 head from the 2 coin tosses. So 1 head, which means R, or the probability of that event to occur, R is actually 1, and the probability of that is 0.05. So in order to calculate that, let's put in P in the 0.5, and N is 2, R is 1. Here P is again 0.5, N is again 2, here again N is 2, R is 1, and R is 1. So put all these values, multiply them and divide them and calculate them, and we get the value of 0.5 as before when calculating by hand. So it is similar to that. So this is how we can use the binomial formula to calculate the probability distribution. So this is here the probability of 1 head that we calculated as an example. Now, on the other hand, we also have a Poisson distribution, and it is used widely in statistics for count data, and is therefore a discrete distribution. And it is used to describe distribution of counts of events, such as when specific events happen randomly in time, and when small particles are distributed randomly in space. So it lies somewhere between simple binomial distribution and continuous distribution. And it assumes that underlying rate is constant. That is very important for it. And to understand the formula, let's look at this. So if the mean number of events that happen in a single period of time is M, so M is the mean number of events that happen in a single period of time, then the probability of R events in a single period of time is, so this is the probability. So R is the number of events that can occur, and E minus M is actually, the E is actually a constant, and that constant is known as a numerical constant, which is equal to 2.718, and values remains the same. So here we have the formula. So put in the value of E, which is 2.7818, put in the value of M, which is 2, so it becomes E minus 2, put in the value of M, so it becomes M and R. So E minus 2 into 2 divided by R. So if we are taking 0, if you are finding out the probability for 0, so it would be 0. Let's suppose if you are talking about heads or tails, so we are saying that there should be no heads, so 0 would be the R. So we put in the value of 0, so 2.78 power minus 2 multiplied by 2, so we get the value is equal to 0.135. And similarly for 1, we put the value of R is equal to 1, or everything else remains the same, and we get the answer of 0.271. So that's how we can use the Poisson distribution to calculate, or Poisson formula to calculate the probability as well. Now here is an example of the Poisson distribution, in which we have different number of events, 0, 1, 2, 3, 4, 5, and by calculating the probability we can actually draw this distribution. And here we can see that mean is equal to 1, because 1 has the highest probability here. So as with binomial distribution, the Poisson distribution takes a different shape with different values of its parameter, which is actually the mean number of events. And here we have another example. Here we can see that mean is 5. So at the level of 5, the probability is the greatest. Similarly, here we can see that the mean is 25. So the probability is highest at 25. So it is dependent. Poisson distribution is pretty much dependent on mean. So when is an exemption from Poisson distribution? If the events do not happen randomly and they are occurring systematically, so the Poisson distribution does not remain valid, or the mean number of events is not constant, it keeps on changing, then once again Poisson distribution is not valid, because it depends on the mean, and we cannot use the Poisson distribution if that is not the case. For example, when counting cells in a volume of blood, the Poisson distribution will only apply if the cells are evenly distributed, that is, the blood sample is well stirred. But if there is an uneven distribution and there are more cells on one and the other, then the probability, it is not the correct way to calculate the probability for that. So Poisson distribution does not fit in that scenario. Now the mean of the Poisson distribution is denoted by M, as well we already discussed when we were using the formula and calculating the distribution. So the mean number of events in single unit time or space is known as M. It turns out that the variance of Poisson distribution is also M. So thus the Poisson distribution is characterized by only one parameter, either the mean or either the variance, because both stands for M. And unlike the binomial distribution, in which it is characterized by two parameters, which one is the probability of success and the other is the sample size. So if you don't have both these parameters and you only have the mean, you can use that mean to calculate or find out the Poisson distribution. So that was all about these two distributions, and I hope you learned something new out of it. In the next upcoming lecture, we're going to talk about the continuous and natural distribution. So stay tuned for more lectures like this. I hope it would be beneficial for you. Thank you very much.